Today we're going to talk about the damped harmonic oscillator. Before we do, let's review the geometry of systems of differential equations. Here are some definitions. Say that we have two functions, f and g, which are functions of three variables, t, x, and y. A two-dimensional first-order system is a system of first-order differential equations of the form dx dt equals f of t, x, and y, and dy dt equals g of t, x, and y. An initial value problem is the extra condition that x of t0 equals x0, while y of t0 equals y0. We'll typically express this initial value problem in terms of two-dimensional vectors involving here a capital Y in terms of lowercase x, comma, lowercase y, and capital F, which is lowercase f, comma, capital lowercase g. We'll say that a vector-valued function, capital Y, is a solution if its components, lowercase x of t and lowercase y of t, satisfy the differential equations you see on your screen. We'll say that the system is autonomous if lowercase f and lowercase g are both independent of time t. Given an autonomous system, a two-dimensional vector y0 is an equilibrium point if f evaluated at y0 is the zero vector. That is, capital Y0 equals lowercase x0, comma, lowercase y0, where f, lowercase f, evaluated at x0, y0 is 0, and lowercase g evaluated at x0, y0 is 0. A constant function, capital Y, equals capital Y0 is an equilibrium solution if capital Y0 is an equilibrium point. To get some intuition behind this, we explain two examples. First, let's consider the predator-prey model. That is, our two-dimensional system dx dt equals alpha x minus beta xy, and dy dt equals negative gamma x plus delta xy. We found before that two equilibrium solutions to this initial value problem are capital Y0 equals the zero vector, 0, 0, and capital N sub x, comma, capital N sub y, where capital N sub x is gamma over delta, and capital N sub y is alpha over beta. More generally, we considered the logistic predator-prey model. This is a system that looks like the predator-prey model, but instead of modeling exponential growth, we modeled logistic growth. We found that the logistic predator-prey model has four equilibrium points, capital Y0. The first is the origin, 0, 0. The second corresponds to the carrying capacity for the variable y, that is, it's the vector 0, comma, m sub y. The third corresponds to the carrying capacity for the variable x, that is, it's the vector m sub x, comma, 0. And the fourth is a point n sub x, comma, m sub x, in terms of rather complicated formulas that you see on your screen. Finally, let's consider more generally an autonomous two-dimensional system d capital Y dt equals capital F evaluated at capital Y. A slope field is a plot where given a point x comma y, we place an arrow at this point in the direction f of xy, comma, g of xy. The idea is given an initial point x0, y0, we follow the arrows to plot out a solution x of t, y of t. An equilibrium point is a point x0, y0 where the arrow f of x0, y0, comma, g of x0, y0 just equals the origin. Today, we're going to discuss the damped harmonic oscillator. Let's begin with the story of an English scientist named Robert Hooke. He was interested in the motions of springs. Here you see some examples of springs that have a mass attached to them. Hooke came up with a law that can be stated as follows. Say that we have a mass m which is attached to a spring. Let's let L denote the length of the spring at time t. If we pull on the spring and stretch it out, then it has a restorative force that causes it to bend back to its initial shape. That is, the restoring force of a spring is proportional to the length it has been stretched. In other words, the restoring force, F sub s, equals negative k times L for some positive constant k. Now, let's say that our same spring hangs from the ceiling. That is, there will be some force F sub g, which equals m times g, that comes from gravity. Since the forces must balance, the spring must stretch to some length L sub 0 under the influence of gravity. That is, will balance the force due to gravity as well as the restorative force due to the spring. We'll find that m sub g minus k times L sub 0 must be 0, or in other words, L sub 0 equals mg over k. The idea here is that the length to which the spring must stretch does depend upon the mass, gravity, and the spring constant k. Notice that if we double the weight, then the length L0 to which the spring stretches will also be doubled. Now let's consider a more general situation. Again, say that we have a mass m which is attached to a spring, and let's let L denote the length of the spring at time t. We're going to consider four forces on this mass m. First, we'll assume that there is a force due to gravity. Newton's law of gravity states that the force is equal to m times g. Second, we'll assume Hooke's law, that is that there's a restoring force on the spring. Hooke's law states that this restoring force is equal to negative k times L for some positive constant k. Third, we're going to assume that there's some type of a damping force. That is, let's say that the mass is in a viscous fluid, one which gives some type of damping. For example, the mass may be affected by air resistance, or this mass m may be in a liquid. Then we'll assume that the force of damping is proportional to the velocity. That is, this force is equal to negative b times dl dt for some constant, positive constant b. And finally, we'll assume that our mass is acted upon by some outside mechanical force, which we'll just write f of t for some function. For example, this may be that someone has reached their hand into the glass and is now manually shaking the mass up and down. Newton's second law of motion states that F equals ma. That is, mass times acceleration should be the sum of the forces. Well, the sum of the forces should be the sum of these four. We have the force due to gravity, which is m times g, the restorative force of the spring, which is negative k times L, the force due to damping, which is negative b times dl dt, and then our external force, F of t. This sum should equal to mass times acceleration, which is m times the second derivative of L with respect to time. Now, let's make some observations here to simplify this expression just a little bit. Let's denote y as the displacement of the mass from the equilibrium length. That is, we know that when there are no forces at play here, except perhaps to gravity, that we should have an equilibrium length L sub 0. Let's let y be the distance we are away from this equilibrium length. Since L sub 0 is a constant, we then see that dy dt is the same as dl dt. Also, we can substitute in the value for L sub 0 as mg over k. Putting all of this together, we see that m times d squared y dt squared is equal to negative k times y minus b times dy dt plus f of t. Bringing everything to one side, we can express this equation as d squared y dt squared plus p times dy dt plus q times y equals 1 over m times capital F. Here p is b over m and q is k over m. We'll give a slightly different way to express this differential equation. For the moment, let's define the velocity v as dy dt. Then we actually have a two-dimensional system of first-order equations. We see that dy dt equals v, but now dv dt, which of course is the same thing as d squared y dt squared, is equal to negative q times y minus p times v plus a function 1 over m times f of t. Ultimately, we'd like to answer this motivating question. What is the solution to this differential equation? Well, to get some intuition behind what the solution should be, let's discuss a couple of limiting cases. First, let's consider the case where there is no damping, that is b is equal to 0, and no external force, that is our function f of t is identically equal to 0. Then our system simplifies to dy dt equals v and dv dt equals negative a constant times y. Essentially, we talked about the slope field of the system in the previous lesson. Here you can see that the slope field sort of suggests that the solution here should be periodic. It should move in this circular fashion. So let's try to do just that. Let's state all of this as a proposition. One solution to this harmonic oscillator is the following vector-valued function. This is capital Y equals the constant A times cosine omega t, comma, negative A omega sine omega t, where omega here is the square root of k over m. To explain why, let's make a guess. That is that our solution should be periodic. Let's say that y of t is a constant capital A times cosine omega t. Now we can take the derivative dy dt, which remembers our velocity v, and we'll find that this is negative omega sine omega t. But now if we take the derivative dv dt, this should be equal to negative k over m times y. But explicitly taking the derivative of v from what's above, we find that this is equal to negative a times omega squared times cosine omega t, which is simply equal to negative omega squared times y. Hence, we'll choose omega squared to be k over m, so that omega is the square root of k over m. Let's consider another limiting case. Let's consider the case where there is damping, that is, our term b does not equal to 0, but there's no external force once again. Our function capital F of t is identically equal to 0. Now this corresponds to the two-dimensional system dy dt equals v, and dv dt equals negative k over m times y minus b over m times v. Remember that what's happening here is that we have a mass m that is attached to a spring, but this mass is embedded in perhaps a liquid in a jar. So while we do expect the spring to bounce up and down, we also expect the liquid to slow down the motion of the spring. Here's a plot of the slope field. You can actually see how this slowing down is taking place. The brown dot will be the initial value of our differential equation. You can see now that as time increases, the arrows cause the brown dot to spiral in towards the blue dot, which in this case is our equilibrium solution. What's happening here is, as things spiral in, we then see that y has to tend to 0. So we expect some type of a decay to show that our solution would then have lower and lower amplitudes. Let's put all of this together into a proposition. One solution to this so-called damped harmonic oscillator is the following vector-valued function. Here, essentially, y of t is a constant times e to the rt times cosine omega t. R here is negative k over 2m, and omega is a slightly different expression from what we had before. Now, let's go ahead and explain why this is true. We're going to make a guess that our function y is a constant times e to the rt times cosine omega t. We can now compute dy dt, which we're calling our velocity v, using the product rule. Finally, we can compute dv dt, which we know is equal to negative q times y minus p times v. And now matching up both sides, we see that the right-hand side is equal to negative 2r times y minus r squared plus omega squared times v. So once we simply combine everything together, we do find that r and omega are what we claimed up above. Thanks very much for watching.